Hello. Today I'd like to talk about the basic concepts of computer graphics, including the screen space, also this world space. These are the today class objectives. At the end of this lecture material, I hope that you can understand the different spaces, also this basic the OpenGL command structure. Then we'll talk about those concepts as an example of this continuous world, this Julia said. Also, these are the review of the prior class. So last time we talked about the various student activities that you should do for taking this course, the program assignment, also the paper video summary submission every week, also the paper presentation. Also we talked about this grading policy. I recommend you to take this prior class and then move on to the lecture. Okay, so this are actually this new hello world in the case of the computer graphics application. So whatever you do, whatever you draw in the screen space, basically you can get, if you get this kind of image, this 2D basically this image actually 2D scale image ranging from this -1, also the -1 to 1 along the x-axis, also y-axis. So basically, you can draw the simple box with just a few of lines of OpenGL code. This is actually some of the examples, drawing this box. Basically here, we're just using the very simple structured OpenGL, which is, even though it is kind of the legacy OpenGL code, the recent one is much more complicated, but I'm using the kind of the old OpenGL code. Still you can actually run and compile with this one. And here actually we assume that it's immediate mode. But anyway, here we just set some color, GL color 3D. This also this the double number. This is actually RGB, red, green, blue color channel. And then basically the RGB actually we got the very high the blue, also the green channel. So that's why actually you got this kind of color. And then we actually specify these 4 vertex, GL vertex 2D. Basically, the 2D is nothing but two-dimensional, two-dimensional with this double type. So here actually basically this is x and y. The -0.5 also -0.5, probably indicating this one, and so on. Basically, this specifying these four corner of this one. And then we combine them with this GL polygon. Basically, here actually we giving the hint to the OpenGL how we can connect this vertex with actually basically these are the vertex actually the vertices of this polygon. And then you can actually, if you actually execute this OpenGL code, you can get this kind of the rectangular shape. So this actually I briefly talk about the OpenGL command syntax. So for example, when I use the GL color 3D, RGB, and then this is actually this the suffix D is indicated here, 64-bit the double, and then basically this OpenGL internal representation. If you are using the C type, it's actually the double, and this OpenGL the type GL double actually. Also there are many other suffix. B actually the sign chair, S is short, and so on. So when you see basically these actually suffix like this, and also before in the prior example we used this kind of the GL color 3F. F is here is a 32-bit float with RGB, but also you can specify some sort of buffer. You can specify this buffer with some sort of array. We actually specify this buffer with RGB value, and then also we can use that buffer pointer to specify the color, GL color 3FV. V is actually a vector, which indicating this kind of the array. So basically, using this kind of buffer for drawing is much more efficient, mainly because that if you are using this buffer, the OpenGL or the GPU architecture know that this actually can be used together, so that actually we can actually cache them in the GPU memory, which is actually more efficient for accessing data. So, but obviously, if you are using this one, it's a bit more complicated. But for the class, we just using simple one. But obviously, the recent one also using this kind of approach. Also, we call it this like the retained mode. We retain the data in the GPU memory and so like that. And another example, here we draw the triangle. We specify color and we specify vertex. We connect them with the GL polygons. basically this actually specifying the three vertex of a triangle. Here actually we use the GL polygon. We basically this actually we actually ask the OpenGL to connect this bodies with polygon. Also there are many other these drawing primitive available in OpenGL. We can actually use this kind of we use the GL polygon here, but more common is actually GL triangles. So if you specify the vertex V0, V1, V2, V3, V4, V5 with the GL triangle, we connect like this. And more actually also the optimized, also advanced one is the GL triangle strip. With the specified the vertices, we actually we create this kind of this triangle or set up the triangle that connected, which is called this triangle strip, and so on. This kind of things also available at actual OpenGL the book, the command the book actually. There also the typical we call this red book. It actually has the red color on the book. But of course, you can use the Google search, and you can also even ask the ChatGPT. You can get lots of information from there. Yet another example. Here, actually, I draw this kind of circle, also specify the color, and then in this case, I use the GL line loop, and then actually here actually I approximate this circle with this kind of a set of the discrete very small line segment. So here I actually specify this every vertex, little this vertices under this circle by using this cosine sign, and then basically these are actually this coordinate representation of this circle, and then we based on that I specify that this GL vertex 2D with x and y. Basically starting from this degree. The I starting from 0 to the 360, I actually convert it to the degree to the radian, and I connect it with the GL line loop. If I go to GL line loop here, if I specify this one, I connect it with the line, right? So based on that, basically I can get this kind of I just specify these little vertices with these 360 vertices and connect them with a line. But you can see that actually it looks like the continuous circle. That's actually one of the main approach how we can actually treat create this kind of continuous representation with the computer. I will get back to as I mentioned before, if we wanted to, this is actually the very simple one, but it's actually a very legacy structure. In other words, it may run very slowly. Then if you want to get an optimized one, recent one, you can ask the ChatGPT to make the recent one. I tried it out, and then I found the actual ChatGPT one quite well. It gave us the very good recent code. Here actually also I'd like to talk about a few of the structure or context of OpenGL. OpenGL actually you can treat it as a kind of state machine. OpenGL maintains various states until you change them. So for example, here I set the color GL color 3D with RGB, but you specify every vertices, right? And then unless I change the color into another one, I actually when I set this one, I actually maintain it at the GPU structure memory, and then when I actually draw also treat the access this vertex, I use the color. Another approach, basically, if you want to change the color for every vertex, you need to call this the GL color for every right before you using this GL vertex. But anyway, this state machine, you set this state, and then when you encounter some another vertices without having this one, then we just we actually basically apply the state again and again. Also, there are many there are actually many state variables. Also, they're referred to some sort of mode. For example, if you want to enable the lighting, you have to enable it. So that's why actually there are some GL enable, disable, that kind of the function. Also, you can even ask what are the actual state variable, what's the state of these variables, like the GL get float. Obviously, you need to give some sort of what kind of mode you want to know. Also, sometimes also you want to know what are the actual error that actually are happening in the GPU side. You can actually call this GL get error, then it will give us some information, which are also very useful for the debugging in the GPU. So this is a very simple one. So I recommend you every time when you call this kind some sort of the GL OpenGL function in this case, GL texture coordinate pointer, and then sometimes actually there it might actually there I'm not going to talk about the details here, but sometimes it may actually have some bug, mainly because of the some sort of the type mismatching between the parameter. Then you need to check this kind of you need to check the error, and then here actually I defined this with this macro, and then in the macro actually it just asking the what are the actually the error you might get, and then it returns some sort of error number, and then if we need to translate this error number into some sort of this error string, then you can get the information what kind of error message what kind of error you actually run into by calling this one. So every time when you call some new OpenGL API, you can actually check the error like this. Also, obviously, you can also if you are using some other recent OpenGL or even DirectX. Basically, OpenGL actually runs on the Linux, also the Windows, PC, Mac, and so on. But actually, if you wanted to run the very efficient the GPU graphics application on Windows, we typically using this DirectX. Then obviously you need to use another API, but you can ask the ChatGPT to translate into this DirectX code. You can do that. And if I'm using some of the recent OpenGL version using this retain mode, they are basically very complicated. Even though I wanted to draw the very simple one. So that's why actually in this course I'd like to talk about main concept, but I actually hide all the little details since it's not really useful for the education. So again, actually, when I show this code, if you want to know the recent OpenGL code or the recent DirectX code, you can ask ChatGPT to translate it. Also, there are even more complicated, also the low level library like the Vulkan. This is one of the recent change. Here actually we can when you are using the OpenGL, it also hides lots of the details in terms lots of the details related to GPU. But actually, since we are using the mobile phone and other ones where we need to get a much more the performance, then sometimes actually many times we need to use the explicit GPU control, which also complicate lots of things. And then as a response to that kind of demand, we got the Vulkan. And this kind of the new API that enable the explicit, streamlined, portable, extensible API, but actually comes with the cost, lots of the details. So here in this course, I'd like to there are lots of the recent technology, but those one recent real-time rendering actually add much more these complex details for high performance, but it's not good for the beginner like you. But that also there are many other recent trends like basically this kind of the one actually assuming very old this kind of the API assume the very fast rendering pipeline, which we'll talk about in the class. But recent one also actually moving away from this more high quality rendering like the physically based rendering. This is kind of commonly used for the creating very high quality movie like this. But now actually, thanks to the very advanced GPU, we can actually even use this kind. You can have this kind of the quality and then quality even on this game. So that's why actually we can also use there are growing demand to use this physically based rendering even for the game. So that's why actually we will talk about I hope that we can save some time by hiding the details of this OpenGL, and then we can also we can study more on this physically based rendering. Also, on top of that, also another recent trend is that there are many AI generation techniques. So I hope that I'd like to prepare some time so that we can talk about some of the recent generative AI. Like this diffusion technology, but much more important is that actually there are lots of things going on even on this kind of very mature field of computer graphics. So actually your motivation, your interest to learn something new about computer graphics, also your participation is very important. That's why that's why I structured this course in a way that you can actually study more actively by giving the student lecture, also the paper presentation. while it might be very difficult or challenging for you. So again, I hope in this class I will focus on fundamental concept that might last in many coming years, and then use the very simple, even though it's a legacy, I use the very simple OpenGL version as a basic teaching tool. And then I wish that I'd like to lead you to find your interest and see this recent research trend. That's why I'd like to give you the chance, opportunity to give you the digital lecture on a small topic of the computer graphics. Also, find the recent paper and then present it. And then also all the students attend those talks and then evaluate, share your feedback. That way we can learn the recent technology. Even though actually I can talk about a lot of the real-time rendering, still a lot of technique actually developed maybe 20 or 30 years ago. But this is actually the physical-based rendering, also the recent AI techniques. I'd like to actually, these are actually very interesting, very promising technology. So I'd like to lead you to look at some of the recent techniques. Okay, so this is actually the class rendering pipeline. So basically, this is actually the algorithmic side. Also, this is actually more intuitive side here. Please look at this one first. Basically, for the rendering for your game or creating movie, we actually specify some sort of the scene, the 3D model with some sort of triangle, and then we set the camera. And then somehow we actually we transform this triangle information of vertex. You see that actually when you specify the triangle or the circle, we specify that vertex, right? Vertex actually. So here actually we specify this vertex, we connect it with the triangle, and then we basically the thinking direction of realizing this graphic application is that we transform those vertex into this kind of camera space, and then this vertex mapping to some location in this image plane. Basically, intuitively speaking, maybe the film in this camera, right? And then once we do that vertex may be mapping to this kind of some vertex here. This is our image that we are looking at here. Maybe one vertex here, another vertex here within this image space, and then we actually fill the triangle, which we call it actually rasterization. We actually identified what are in between the pixel within this triangle, and then we compute the color. So basically, that's that kind of intuitive structure, starting from the 3D model into the camera space. And also this a pixel color here in the image space. So there are some sort of the change from we specify those information with CPU. Since we are using OpenGL, then we execute those kind of API with CPU, right, with this vertex, and then we actually send that vertex information to the GPU, graphical processing unit, NVIDIA chip, right, and then we actually transform those vertex, which we call it vertex processing. And then here at that point, actually, basically the data structure here actually nothing but pixel information. Sometimes also we call it fragment. Then at that stage, actually, all those operations run on this pixel processing or the fragment processing. Then we got this kind of the result. So this intuitive structure here for any kind of graphic application. This kind of data structure or the algorithmic side of how the data or actually transform from the CPU to GPU, also this vertex processing and pixel processing. This is actually implemented in the various software and hardware of the computer graphics. But if you look at this is one of the recent OpenGL this rendering pipeline. So basically there are many steps, right? We specify vertex triangle, and these are the vertex processing, vertex shader, tessellation, geometric shader. Then at some point actually we got if we run through the rasterization, we got this fragment pixel, and then also there are many other steps here. So basically there are lots of steps, but in this class I'd like to give you the high levels of those steps, and then I'd like to spend some time on talking about the recent technology. Also, there are many other ones. So here, actually, we talk about OpenGL, also Vulkan, which is more this low level, providing more low level control on the GPU. But also, there are many the game rendering engines. You might heard about Unreal Engine, Unity. Directly accessing OpenGL is very difficult. So that's why actually these kinds of company and tools actually build more advanced APIs. And then user can basically game developer typically use this kind of game engine to design the game and then game in a more efficient way. Also there also sometimes also we need to do the more sometimes like also we need to use the very low level the shader. This actually shade also this kind of the shading language GLSL for OpenGL. Also there another information for DirectX. This the shading language is nothing but we actually some sort of the computing the program that runs on the GPU directly to perform some sort of graphic application. Sometimes actually we might have time to talk about this one. Here actually GPU evolved in a way that to execute this kind of the GPU the graphics application. But as you know, the GPU actually keep evolve and it can now enable the very generous, more general these programs like the CPU, right? So that's why another tools like CUDA, which is actually enable the GPU general purpose computing tool, the language on the GPU actually. So basically now actually we can use the GPU like CPU through this kind of language tool. That's why actually we got this kind of the approach maybe 20 years ago, and then maybe more than 10 years ago actually. Now actually some people realize that we can even use the deep learning with this GPU. So now that's why we got the era of the recent deep learning era. So that's kind of the structure or kind of ecosystem of the many tools, the language of GPU the field. So I talked about the very simple OpenGL example. I talked about some of the other related tools. Now I'd like to talk about some of the concrete example here. Here I'd like to define some sort of Julius, which is nothing but some sort of this fractal function. Basically, this is here actually I'm going to show you this OpenGL example. It's nothing but some very simple visualization tool of the fractal function. Fractal is nothing but just a simple iterative function defined over the imaginary plane. And then, as you can see, somehow in here, and somehow we visualize the fractal function. It has a very chaotic behavior. I mean, the very small change along the x and y. Here, actually, this x and y corresponding to some sort of the real and image plane of the complex number. You can see there very little change has this kind of the very dramatic effect. So obviously we can actually understand this fractal, but it might be better if we can actually have this kind of visualization tool. Let me actually run this tool here. So if I run this demo, this is the fractal one here. And then if I click the left mouse button, I can zoom in here. I can keep zooming. You can see there. Even though I can keep zooming in, you can see the same pattern appearing again and again. If I click the right button, actually zoom out. I can actually make it larger and so on. Yeah, that's it. And I can actually change it like this. Yeah, I can also I can actually actually support all kinds of the Windows operations. Okay, so now I'd like to see how we can do that. First of all, how we can define the Julia set. This definition. Given some number c in the complex plane, you might recall that complex plane like this has the real component, also this imaginary component, two tuples, and then is given by this function. Starting from the Julia set at this given c, also we starting from the some value p, and then we actually evaluate this iterative function. Starting from the pi, we actually take the square and then we adding c, and then we got the next value. We keep doing that. But if this series converges to the fixed limit, then we actually this is in the Julia set. Otherwise, if there's some given some sort of this p, if this diverge along with this sequence, then it's not on the Julia set. The very simple one. But we'd like to see how the Julia set are in this kind of converge in some sort of limit or the diverge. Basically, this converged region actually we give this black color. For other region, for this diverged region, we give some sort of color. You can see that very small change, some sequence result in this converged one, another one actually diverge. So in the case of real number, basically if we just consider real number, it's very simple, right? So also to assume that C is a very simple structure, the 0, and P is just a real number, then the Julia set series reduced to the like this, and then it's very simple, right? For the x0, then it will be, if we keep doing this one, it will be limit actually converge to 0, right? Further this one, further some number bigger than 1, obviously if we take this one, it will be diverge. We know that, right? So at the case, a very simple structure, when C is the 0, 0, then for the real number, the magnitude of the real number is bigger than 1, the series diverge, right? For the complex number, the magnitude of the real the P, the complex number is bigger than 2, then the series diverge. Actually, this 2 is the kind of loose bond. So then, basically, you can see that the black one, for the converged one, we give the black color here, which are in the Julia set. For other one, it's not on the Julia set, but we somehow give the color, so we actually see we can see which one actually in the black and others not in the black one. So here, this is actually some sort of some code of this that code that the Julia set of visualization. This is actually some class of the complex number consisting of the real and imaginary part. This actually Julia set function. We actually we provide the P and C with the sum of the I and R. This is actually given with the reference value, indicating that when you change the value of I and R within this function, it actually change this globally. And then here actually we need to see whether the series will be diverged or not, right? So basically we actually iterating this sequence with up to this max iteration, and then we keep doing that. We evaluate this Julia set series, and then this is actually the root square of basically the squared magnitude of this complex number. And then at some point, we know that actually this root squares bigger than 4. We know that it's diverged, right? So then we will actually break it, and then we set the R with some number I. I mean, maybe we identify that it will be diverged with maybe 10 iterations, right? And based on that I and R, we actually set some color. Even though I didn't show that how we can set the color here. And then if for another case, even though we actually keep iterating until the max iteration 256, then this root square less than 4, then we just treat that it's converged, and then we are reaching there, and then we will set the computer that R over there. And for that cases, it will be we know that I actually turn out to be this max number. Then we know that that's there will be the converged one, and then we give the black color. So that's why actually that's how we actually wonder how actually implement the Julia set example. Then the question is that the wall space of Julia set is basically the infinite, right? Then how can in the end we wanted to, even though the Julia set defined on the infinite space of the imaginary space, imaginary number, in the end our screen space only limits the region, right? So basically we need to define a mapping from our desired world view to our screen. I mean basically there are infinite space of the Julia set function, but we need to somehow define a particular region and then map that region to our screen of our Julia set example. That's the typical computer graphics, the issue of the computer graphics application. So in other words, we define some sort of the world. In this case, Julia said world is the actually imaginary space, this infinite space. But obviously, we cannot visualize all of them in one screen, right? So that's why typically we set the camera here. We set the camera here. In this case, we only look at this portion of the world through our camera, and then we actually mapping we map the world, the color of the world into this kind of the window region that we are using here within this monitor screen. Basically, when you are looking at this kind of screen of the PowerPoint slide, basically we actually mapping that PowerPoint content into this kind of the image, right? That's what we are doing in this kind of the example. That's the typical setting of computer graphics application. We only map this region to here, the window space here in the monitor. First of all, to answer this one, we need to define the screen space. In the end, this window is nothing screen space, right? Consists of the pixel, right? Screen space nothing but this graph. I mean, basically, we can represent this kind of graphical image, right? By setting the color for a set of the discrete samples. We call it this pixel, right? And then this pixel actually display on the screen in a typical window, right? This pixel nothing but just 2D array, and then we can specify this kind of index. Also, we call it screen space coordinate. So typically, depending on the cases, typically we call it this 0,0 here. This is actually the kind of index number of this 2D array, the x and y, 0 and 0. Along this x-axis, we got this coordinate. This width is actually the width of this image, right? This is we call it typical screen space. But depending on your cases, this convention different. For example, for typical this kind of image, we call this kind of convention. Basically starting from 0, we actually increasing that x and y value along that one, right? But typical OpenGL screen space, we typically set this 0, and then we increasing this x and y from there. So you should, before you actually accessing this kind of low level coordinate, you should know this kind of convention. Also, typically we introduce here when you actually mapping some portion of walls through they are visible from the camera to this screen space within the window. We typically introduce another intermediate space, which is this normalized device coordinate (NDC). This is the kind you can treat that this kind of intermediate rendering space. Also, we sometimes call this canonical screen space. That starts from the that range from the -1 to 1. So early on, I already showed this kind of the normalized device coordinate, also canonical screen space. If you don't specify any camera and other information, other one, this is your default space, the NDC. So why actually using NDC? It simplifies lots of the rendering operation, which we will talk about later on, clipping and many other ones. Basically, that's why actually we introduced this one, but we will talk about this kind of low-level detail issue later on. For now, basically, before we converting to this viewable region to screen space, we typically mapping through this NDC. Then the question is that typically we set we know the world position of here in the world space. For example, when you specify some chair or some vertex of that triangle in the world space, we know that position in the world space, right? The question is what are the location? When you set the camera that way, what are the location in the ND space from that position? Here actually we call it XW. This is the coordinate, the mapping to here is we call it XN in the ND space. And then also what are the actually screen space, the pixel index in the screen space here. We call it X sub S. Now let's look at this part first. So here, to know their relationship, we can actually align them together like this, right? This actually world coordinate. Basically, here actually suppose that we can look at in terms of world region, we can only look at this portion of the world that's starting from the left and right, bottom and top in the world space. That's actually the one. Along the x-axis, this is the world dot L left, the right. but this should be the mapping to the -1 to 1 in the any space, right? That's the assume that that's what we wanted, that's what we wanted to do. Same thing in the y-axis, bottom and top -1 to 1 in the y-axis. Then given this one, we can set up the. Then the question is that given the world coordinate, what's the this coordinate, right? Then based on this one, here we wanted to maintain the ratio. The ratio of the world space also in the any space. So to do that, based on that assumption, we can set up this this relationship, which is nothing but if we look at the ratio in the world space, given the relationship between the L and R, and then we wanted to we look at the ratio between L and R with the L to the this the XW, right? We wanted to maintain the ratio between the whole width and the width of the point with this, even though in the empty space. Then this L and R mapping to the -1 to 1, so we got this one, and then the ratio at the empty space xn minus the -1. So we still maintain the ratio between here and there in the world space or the empty space. Based on that, then we can set up this equation. Then if we actually reformulating, then we can get this information. If we starting from if we put the xw, then we got the xn, right? Also if we look at this equation like this, then we actually multiply a to the world coordinate, then we are just adding this one, right? So you can see that in the end, it's a very simple structure. Basically, given the world coordinate, we multiply something, adding something, right? But if we actually had many vertex within this world space, for every vertex, every coordinate, we have to apply this one, right? You can see that this is very simple linear operations, right? That's why the GPU evolved in a way to efficiently process this one. Also, it turns out that recent deep learning algorithm also rely upon this simple linear operation. That's why the GPU actually is very widely used in even deep learning. Same approach we can apply to the transforming from the NDIS to the screen space. This one that I'm talking about here, from NDIS to the here window. Same approach, then we can set up this one. In the end, we can also set up. We can get the same approach. We can same setup, and then we can get the same thing. Given this the xn, we can get the coordinate in the screen space. That's it. So I talked about the base OpenGL structure, a little bit about OpenGL. Also, I talked about the Julia set, and then now I'm actually giving the first programming assignment. I found already TA upload the spec of the PA1. You can just download the spec, look at this one, and download the code and compile and linking and play with it. So basically the graphic running the graphics application require you need to download some library and so on. It actually understanding code it's not that difficult, but there are many other additional ones like the connecting the library correctly and so on. So that might take a lot of time for you. So that's why I recommend you to start early. And then basically I'm giving you the very simple operation here. For example, typically in the spec actually we got this kind of reshape function. The reshape actually opened when you actually change the window size. For example, here actually I change the window size, like make it bigger, right? Also that I can make it smaller. Every time when I actually changing this one, then basically the screen space actually the region of the screen space actually change, right? So that's why the region of space change actually through this GL viewport. So but in the existing code we got this one. Somehow here actually we set this W and H actually this width and height of available this screen space. Based on that one, we actually set the screen space, the image space with the GL viewport, and then we set the visible world region like this. We set based on this one, we set the left hand R and so on, top and bottom and so on. But I want to change the reshape function like this. Basically here, once I got the W and H from available screen space, I just set the W and H. I just cancel this one. So basically, it assumes that then based on that, I can actually maintain. I wanted to maintain the ratio of the width and height. I actually apply the ratio within the visible world space. But if I just changing this one, I got this kind of error. So obviously I cannot able to alter this available screen space, right? So I need to change something in the display. But if you actually follow the specs, you can see what can be done to fix this one. But actually, I'd like to. It's not that big. It's not that the really difficult one. But if you follow the basic structure, you can figure it out. Also, you can even ask the TA or the ChatGPT. But the main reason why I'm giving the PA1 is that just the compiling and linking and then the running is actually that's the most important one. Just fixing this one is not really difficult. But anyway, also before when I give this computer graphics course at the 2020, I actually had another separate course, separate lecture about basic OpenGL structure. But actually, I'm not going to talk about this one again. So basically, if you want to know more about the OpenGL structure, I recommend you to look at that YouTube lecture that I gave in 2020. I think that TA already linked that YouTube the lecture in our homepage, and that lecture based on the Visual Studio 2015. But I found that TA will talk about the recent Visual Studio, like the Visual Studio 2020 with another library, NuGet and the Freegalot and so on. But why I'm doing that? Why I'm actually not teaching the basic OpenGL structure again? Basically, as I mentioned before, I'd like to cut down low-level details related to OpenGL. I think that there are lots of more important concepts in the computer graphics. So that's why I'm gonna save some time here, so that later on I can spend more time on this recent AI technique, also the Monte Carlo ray tracing, which will be the main ingredient for the physically based rendering. So overall this year, I'm not going to talk about the low-level details, but sometimes if you wanted to know more about the low-level details, I recommend you to look at my book available at the homepage, and then also you can watch this prior the lecture that I gave the 2020. It will contain lots of the low-level details. Okay, so by now I hope that you can understand the concept of different spaces and the basic how we can actually transform from here to there. And also I talked about the basic OpenGL command. Also I talked about as an example, I talked about continuous world that we cannot visualize everything in the screen space, but to visualize we set the camera, and then we talked about how we map the viewable region into the image space. Okay, that's it. And then if you have any question, you can write down the KLMS. Also, you can come up with the one question and submit it at the submission site that are linked in the homepage. Also, I look at those command, and then most of the case I give the score of 1. But sometimes I found a very interesting comment that even surprised me. I give the 2. But you don't need to try to come up with that kind of question that can receive the 2. It doesn't make big difference for your grading. Just write down the question that naturally arising to you, and then basically you need to submit 2 times during the whole semester. I found some students actually do the multiplication in 1 time, but that's just they kind of the one submission just treated as once. So you need to, throughout the semester, you need to submit 2 times. Also go over the next lecture slide before watching this YouTube video, and then you need to watch the 2 SIGGRAPH Asia and many other top tier conference video, broad video, and submit your summary before every Monday class. So this time, the next Monday, before the next Monday class, you need to actually submit the 2 of them. Just you can submit it through the online. I already showed it before. Let me get back to that again. Let me show the homepage again. If you go to the homepage, this one, then basically this question submission form, you can submit your the question here. If you write down, if you want to know the interaction, if you know the answer, you can write down you can share the question at the KLMS, and I or the TA will respond to them, and then you can just copy and paste the question and submit it here, so that actually TA can count how many times you can actually submit question. Obviously, if you want to ask more, you can write down. You can keep writing question on the KLMS. And it's the paper summary, the submission form. You need to actually write down you need to submit too. Further, this the summary. You can actually you can choose the sub. You can actually in the end you need to present the paper. Somehow you need to present the paper recent one. So between the two along this region 2018 2024. And then that's why actually for this one you need to actually you need to go over I'd like to encourage you to go over recent paper and then write down their summary here to submission. Okay. For summary, just the simple one, just one paragraph. English and Korean is fine. Do not use the ChatGPT. I mean, you can refine your writing with ChatGPT, but you are the one who actually summarize this one. Also, this is actually another homework. You need to go over the introduction, also the chapter 1, chapter 2, class rendering pipeline. I cannot talk about low level details here, but if you go there are lots of more detailed information. If you click this one and here actually the whole book here, but if you click here the chapter 1, this is introduction here, and there are lots of information about introduction here that I talked about in the class, and also the chapter 2. This should be the chapter 2 class rendering pipeline. So then, yeah, you can get some of the information here actually. This part 1, actually chapter 2, yeah. So also you can also open whole book. Then you can see what are the chapter 1 and chapter 2 here, the rendering pipeline here. Click the render. Yeah, this is actually chapter 2 that we talked about in the class here today. Okay. This is the homework. If there's homework, it means that might be the quiz. And basically, typically at the 2020, next time actually I talked about the basic OpenGL programming, but this time actually I'll just review to watch the lecture, the basic OpenGL structure YouTube. But if you can do the OpenGL programming, the PA1 without watching this one, you don't need to watch this one. If you need some more information, actually you can watch this one. But this year, I'll actually skip the low level details about OpenGL. I directly go to the 2D imaging and transformation. I will talk about this one later on. Okay, so then that's it today, and see you the next Monday. Bye.